Okay, this is class 14, which is the last class session. I'm actually recording this off-site, so we're not doing this in the typical class session, so you can see this when I post the video with the other ones. That's why if you're looking at the time above, you might see it at a couple of different times, because I'll probably record this over a couple of sessions and concatenate them together. So anyway, tonight we are going to look at high-performance TensorFlow. This includes the GPU. So with GPUs, you can definitely get additional processing power for certain types of applications. Not all application types will benefit from GPUs. GPUs were meant mainly for video games, but a lot of the math that goes behind the 3D rendering can also be used in a variety of different computing platforms. This is typically called GPGPUs, General Purpose GPU. And GPU is Graphical Processing Unit, that's your graphics card. This is almost like back in the day they used to have math coprocessors for computers. The GPU becomes something like that. If you need the additional processing power for mathematics, it used to be you'd buy a coprocessor. Now those haven't existed really since I guess the 386s. But you're able to augment the processing power, or graphics power definitely, with the GPU. So I'm going to show you some of the different types of GPUs you can use. I'm going to show you how you actually install the GPU, at least at a high level, for TensorFlow, because you've got to make sure that you've got all the drivers correct, or it's simply not going to work. We'll talk about the different types of GPU, because there's a variety of types of GPU that you can buy, and some are certainly better for deep learning than others. And I'll show you the types of GPU that I make use of and how it can actually speed up your deep learning. Depending on the type of data that you have and how parallelizable it is, it can speed it up considerably. The example that I will show running one of the same examples that we looked at earlier in class, we'll see that without a GPU it takes about an hour and a half. With a GPU it takes about half an hour. So that's about 1/3 of the processing time. And that's using just the GPU type that is available on a Macintosh Retina class machine anyway. So the page that I have here for the class notes, I've basically just put together a variety of links to show you some of the data that you want to look at. As far as using GPUs with TensorFlow, at this point, which is nearly the end of the year in 2016, TensorFlow does not have real good support for the Windows platform. You can use it as a Docker image. I suspect they'll improve that in the future. So if you're watching this video at some point much later than 2016, hopefully the road is easier for Windows compatibility with TensorFlow. But at this point, TensorFlow supports mainly Macintosh and Linux. And I've used GPUs on TensorFlow on Mac, on my Retina Macintosh's built-in GPU, which is a 650M. And then I've also used it together with the with Amazon AWS, which I was running in Linux. And some of the Amazon GPU instances do have a variety of GPUs available that you can make use of. So let's look at the types of GPU that you can make use of. The two major players in this space are Nvidia and AMD. So Nvidia definitely seems to have the greater support among software programs. Nvidia uses a standard called CUDA. CUDA, if you hear of this, it's in a CUDA. It is specifically targeted at it's the low-level architecture of Nvidia GPUs. There's a second standard, a more open standard, that supports, I've seen it supported on Intel GPUs, on AMD, and also Nvidia, and it's called OpenCL. I see it less popularly supported, and I have seen some examples of OpenCL being less performant than a comparable CUDA application when running on the same hardware. So I've always used mainly Nvidia technology, and that is what is certainly at this point supported best for TensorFlow, is again in late 2016. TensorFlow does not have support for anything other than CUDA, so really anything other than Nvidia. So just to show you some of these different video cards that you can look at for this, this is the Passmark website. You can see the URL at the top. I highly recommend looking at this to get an idea of the current GPUs. This test, much like an IQ test, you have to realize there's a lot of different types of intelligence. There's also a lot of different applications for GPUs. This is much more targeted at video games, but it's a good proxy for how well it's going to work on something else. You can see right now, at this date, the Nvidia Titan X is the king of the stack as far as GPUs. This uses the very new Pascal architecture, at least new at this point. If you're going to buy a GPU for TensorFlow and $1,500 is US dollars is not an issue, that is probably the one to get. Then you can see very much Nvidia is this is a member of their GeForce line, and then there's also the Quadros, which usually land pretty high on this list. If you just go to Nvidia, you'll see that really they have three main classes. So if you click on their products link and processors, you'll see there's GeForce. GeForce are your gamer GPUs. This is meant for video games, and if all you want to do is video games, this is probably the best you can do. The GeForce is also, though, at least among individuals, probably the best or the most commonly purchased GPU for GPGPU as well. So for TensorFlow, if you want to get the best overall performance and you're not buying a specific workstation for it, this is quite possibly your best option. The next class is Quadro. These are workstation sort of class GPUs. They're often configured with very specific drivers that are engineered for the sorts of applications that you're going to use for this. I do not believe there's any specific tying with TensorFlow and Quadro, so I don't know that Quadro is going to necessarily give you any advantage in TensorFlow other than what the GeForce would do. I really haven't used Quadro a whole lot. Tegra is mobile. We'll skip that sort of for a moment. And then there's also Tesla. Tesla is essentially their server class GPUs, and these deal mainly in large grids of computers or in the back office. If you're using Amazon AWS, this is the GPU type that you're going to be using because Amazon is definitely enterprise computing. So these are really the three that you're looking at. Like I said, GeForce and Tesla are the two ones that I've primarily worked with. And the main difference between a gamer GPU, so something like a GeForce, and Tesla is if you think about what a gaming GPU does, it's actually very different than a scientific GPU. So a gaming GPU has to do extremely intense mathematics and do it extremely fast because it's displaying frames per second. So frames per second are what on the most high-end video games are how they measure the force or the processing power of a GPU, at least for games. But if you think about the differences between gaming and scientific processing, it's largely a one-way street to the GPU. So data goes to the GPU but doesn't really come back for a game. Data needs to come back for the scientific computing. So you're sending data off to the GPU, you're loading it up with your data sets for deep learning, just like you're loading it up with shades and other data that the gaming GPU is going to use. But nothing comes back from a video game. It displays one frame and that's it, and the new data comes in and it goes on to the next frame. So that's one difference. The bandwidth of data coming back and forth between a GPU, they optimize this more on the higher end, more scientific based ones like the Quadro and the Tesla. Another big difference for this is the precision, the number of decimal places you can deal with in the GPU. GeForce and the other ones are faster at less precise numbers, so you'll usually use the floats rather than the doubles when you're dealing with graphics. For certain types of scientific computing, the precision is very important. However, for deep learning, the precision is much less important. Typically, in TensorFlow, at least at this point, they recommend using 32-bit floating point numbers. That's where the main support is at, because the precision is simply not needed as much. These are adaptive algorithms that you're using in deep learning. Errors abound all over the place as you're trying to optimize your weight matrix. So if one weight's a little off because of a rounding error, it's really not going to hurt you that bad. So for scientific computing, at least for deep learning, the lack of precision doesn't tend to be as much of a problem. Another huge reason to use 32-bit over 64-bit is the more of your data set that you can get into memory, the better. The faster your training is going to go. So if you go from 64-bit to 32-bit, that effectively doubles the amount of data that can go into the memory right there. So that's quite valuable. So definitely look at the Passmark site to get an idea when you're looking to buy a GPU. Typically, you'll want to find probably one of the GeForces if you're just going largely general purpose, and you might want to use it for gaming as well. I don't know that the Quadros and the Tesla are necessarily, I guess in theory you can play a video game on it, but it's just not really necessarily built for that. So let's look at basically, and the Titan is typically considered part of the GeForce line. So let's look at that one. If you see that on Amazon, if you just basically do a search for it, you'll see it is literally $1,500. So it's a very advanced GPU. It's 12 gigabytes in RAM. That's important. So that, I mean, the GPU on my Macintosh PowerBook, let me see if they give any of the specs for this. Not really. So, but anyway, it's got quite a few cores. It can process a lot of data simultaneously. We'll see some of the other specs on that as we look at some of the other ones. And you see the one that I use to actually run this. I have not actually purchased one of these or tried this out. Lately, I have been going more towards making use of Amazon Elastic Cloud to run this sort of thing. rather than building bigger and bigger and more powerful towers for myself to use, I don't tend to use them nonstop, so I find it more cost effective lately to use AWS to run these kind of compute jobs when I do this. And also I use more laptops, and it's very convenient to kick off a job on AWS and just let it be running. I can change locations, close the laptop up, connect back in. It was running while I was gone, and it continues to run. So that's useful. If you do want to use Macintosh or laptops for this type of thing, there are GPU enclosures. One of them that I've been hearing a lot about lately is the Bison, which it's a pretty cool concept. You basically just hook this external enclosure into your computer, and now you have an external GPU. Now the video connector is actually out the back of this, so you're literally putting a GPU into there, and you can run a second monitor on that GPU, but most likely you're using it just for compute power, and it connects into your laptop. I have not worked with these. I find this to be a very interesting concept, especially since laptops are becoming so common and so powerful in their own right, but this is certainly something you could look at if you want to use laptop and you want to use high-end GPUs. One of the reasons too that if you look at what the GPUs look like going into them, these things are real beasts as far as what they require. They take 2 slots in your computer. They typically require upgraded 1,000-watt or so power supplies, and they generate a lot of heat. So they have very much a fan that is cooling them. That's why inherently you can only get so powerful of a GPU into your computer. There are computers that have laptops that have very high-end sort of GPUs in it. If you want sort of the ultimate in GPU and to some degree mobility, I don't know that I would call this necessarily that mobile, but the System 76 machines, these are computers with pre-configured Ubuntu Linux in it, but look at this monster. It's a very cool laptop, but look how thick it is. This is not at all going for the same sort of idea as what you're going for with the Macintoshes, with the cult of thinness, so to speak. But you can get 64 gigabytes of RAM on this, and you can get pretty high-end GPUs installed on it. I mean, an 8 gigabyte GPU on a mobile device. Now, as they show it, pretty much it's sitting in a lab somewhere. You're not necessarily grabbing this and running with it. I don't know that I would want to go through airport security with this, but in theory you could. So then the next one up is the Quadros. Again, they're big old GPUs that are going to fit into your computer. This one has 12 gigabytes of RAM. This is workstation class, so this has the driver support that you might be looking for if you're wanting to use this with video production or something else. I don't know that this is going to buy you all that much with TensorFlow. The speeds pulling data back from it are probably going to be superior than the GeForces, but I have not found that using high precision on deep learning has necessarily helped me all that much. You'll notice the price is considerably different. It's $3,200, so it's much more expensive. You will, if you're buying high-end workstations designs for specific tasks, so designed for specific video production software or other products, they may come bundled with this already in it, and the drivers are such that you're guaranteed compatibility. And actually, guaranteed compatibility is a good thing, because going on your own, I mean creating your own computer, trying to get the GPU working, trying to get all the drivers happy with each other, is not an easy task. It typically takes me at least a couple of hours of going through all sorts of Stack Overflow posts and other things to actually get the GPU on my computer functioning with TensorFlow and everything playing nice together. Once everything is playing nice together, it's very easy to use, and it's used largely automatic with TensorFlow. So then the next class up is the Tesla. And if you look at the Teslas, you can see we've jumped another whole pricing range. Now you're in about $4,000. I don't know that I would buy a Tesla completely just on my own. Usually these come bundled with machines that you're specifically buying for the data center. And these machines, Nvidia makes machines of their own. I think they license them through other manufacturers. But if you're buying a Tesla, most likely you're buying it bundled in with a high-end server class machine, and the drivers and all of that stuff is already taken care of for you, because you're basically buying one machine just sort of off the rack to put into your rack at your data center. So anyway, these are the three primary types of, or families anyway, in the Nvidia line. Now if you're doing AMD, you're not going to have as much luck, because the TensorFlow just does not support OpenCL at this point. There's discussion on it, and that's been going on for some time, but as of version 0.12 of TensorFlow, they do not currently have that. Now, the bad news on the Macintosh side is if you have a Retina class Macintosh, you most likely, if you have one of the older ones, you can do that, because if you go to my About This Mac, and I do my system report where it tells me about my GPU. So this is a Retina Macintosh. I bought this Mac in about 2014, and Mac really did not update their MacBook Pros for quite a few years. And in 2016, late 2016, they did update it. But if you look at mine, which is the older one, so I don't have that fancy little LED touch bar that's just above the keyboard that got rid of the function keys. So that's the one feature I'm missing, but I do have this. I do have USB ports, and I do have function keys, and I do have an Nvidia GPU. They switched on the newer Macs to MacBook Pros to AMD, which is very unfortunate, because now you can't do CUDA on them. You're limited to just OpenCL. So I was somewhat disappointed with that. So I'm definitely not rushing out to the store to buy that latest Mac, because basically, as I see it, I will gain the little touch bar that I'm not entirely sure what's for, but I'll lose function keys, I will lose my headphone jack, and I will lose my USB ports. And I will lose my ability to run TensorFlow with a GPU on my Mac. So eventually I'll have to upgrade this machine. But System 76 and Ubuntu is looking better and better kind of every day. But we'll see what Mac does with the upgrade paths. I hope they offer more Nvidia options. Unfortunately, they don't on the Mac Pro, the kind of trash can shaped desktop computer that they have. But anyway, that is those are your options for setting up a computer that has this. And interestingly, you do notice that the Mac Retinas, they are actually dual GPU. So unless you're running something high-end, it will tend to use the Intel HD 4000, which is really just the display sort of GPU for the Macintosh Retinas, anyway. Okay, I'm going to show you a couple of slides, or several slides, from a presentation that I did for the St. Louis Java Users Group a little while back. Now, this was focused more on GPU programming in Java using OpenCL. So for TensorFlow, we're talking more about CUDA and using Python. But a lot of the concepts that that my slides were designed to demonstrate are pretty much the same, and we'll skip quite a few of the Java related ones. So this is a condensed, more Java CUDA specific version of this, but I just wanted to talk about GPU technology just overall. And you know who I am, so we can skip the introductory machines. But GPGPU is what we're talking about. This is general purpose computing on graphic processing units. You're using the GPU to greatly speed up certain parts of computer programs. It won't speed up everything. On certain TensorFlow neural networks, particularly if it's small, if the data are small and the networks are small, you will not see as much speed up. It might even go slower running it on the GPU. This is very much the way TensorFlow does it. You're either running on the GPU or you're running on the CPU. Now you can use threading and do both, which is somewhat interesting. So you could have one whole task. They don't really work together. You can't really use the CPU and GPU together, at least at this point. But if you're training multiple neural networks, you can, using threading, run sort of one on each, and really make the fans in your computer go crazy. So this is... and you can also, like they say there, you can use multiple GPUs as well. I haven't done as much with that, but you can certainly do that, where when we look at some of the AWS stuff, there's an instance that I think has 8 or 16 or something like that GPUs, so it's fairly expensive to rent per hour, but that is an option. So I really try not to do this sort of thing, but this is where you literally build the computer and you stack all sorts of GPUs. I mean, look at that. They've got 1, 2, 3, 4, 5, 6, maybe 6 GPUs. No, actually 7. Okay, so I do have that written. And look how much power that's drawing. Almost 3,000 watts of power. So this is the Fastra 2 desktop supercomputer. It's built by the University of Antwerp. And it was built all with gamer hardware. Now this is a little bit dated. These are some older GPUs that they used in here, but this is really the sort of science project-y look if you try to use a lot of high-end GPUs. They had to physically modify that case with a hacksaw to get all of those in there from what they were saying. They also had to get a specific driver update made just for them from Nvidia, which fortunately they were... I'm not sure if they were using Nvidia or if they were using a different one, but I remember reading about how they installed that. They had to use. It was not easy to get that working. So they showed some benchmarks here. They were using an i7, fairly slow. You can see the green. This is not deep learning. This is computed tomography, so it's sort of a medical CT scan sort of technology, but you can see that even that 512 core cluster, where they had several computers all working together, they were able to get considerably more speed out of the GPU version, and it's not a cluster, it's just one machine sitting there, so it's a desktop supercomputer. And the idea here is this is a specific application that was very much suited towards GPU processing. Not everything is that well suited. And this is like I talked about before. There's the 3 classes. There's the GeForce. These are your gamer GPUs. These are probably the most popular with people using them with TensorFlow. You'll use sort of a GPU. You'll use, a GeForce. That way, if you really do want to play a video game, it's going to be awesome for that too. The Titan X currently, and if you're watching this video much later than 2016, that will date it, but at this point, that was the top of the line GPU. Then there's also Quadros and Teslas. If you want to use GPUs in a business environment, you're probably going to want to deal with Tesla, maybe on AWS, because now you don't have to have your support infrastructure people configuring GPUs in traditionally business class computers, which they might not be equipped to do. But if it's just cloud computing, it's just a different type of Amazon instance, and you can make use of it. And I touched on this a little bit before, but how a game uses a GPU is very different than how scientific computing uses it. 32-bit floating is typically good enough. Scientific computing often does need that 64-bit double, but deep learning, at least TensorFlow, recommends very much using the 32-bit so you can get more into memory. Computation time is typically very short, so frame by frame by frame. This is something you do have to watch out for too. Usually the people who wrote the kernels that you're executing will have taken care of this for you, but you need to break your computing into very short packets of time because, and this is a driver issue, but if you're using the GeForce and Windows, if basically when a GPU, so if you've only got one in your computer, when you're using it for floating point calculation for deep learning, when you're running one kernel, until that kernel comes back, your display is locked up. So if you're trying to move the mouse around, won't move. It'll be stuck. It'll look like your computer is froze. And ill-behaving games will sometimes lock up and crash the graphics card, because you can crash the graphics card. It's going to need a reboot at that point, and typically how you reboot that is by turning the computer on and off. Well, Windows doesn't like this. They feel like that makes the Windows operating system look unstable when it's really not their fault. It was the GPU in the game that locked up. So what Windows actually does is it monitors the GPU, and if it appears to have froze, it will bounce. It'll reboot the GPU card, and that'll kill your kernel that was running. So if you take too long processing, that'll be a real issue. Now on the Tesla cards and the more advanced drivers, because they know that you're going to be doing this, you don't face this problem. So that's another advantage to the higher end ones. Most modern deep learning packages that are built for this will it will simply they just break it up into smaller chunks so that you don't run into that problem. So data rarely returns. Like I said earlier, you're rendering a frame and that's it. It's not going to come back. Now GPU holds textures between relevant frames. The whole texturing process that you can see in CUDA, all those calls, are not terribly useful for mathematical computing. Math is important, but branching is not. So when your if statements become a real problem when you're trying to write code that actually executes on the GPU. Now, if you're just using TensorFlow and you're not writing the actual code going onto the GPU, this is much less of a problem. But if statements absolutely do not work well on a GPU for the code that you're running actually on the GPU. If you use them in your Python app, that's not a problem. So this is the GPU that I was using at the time. Quite dated, the GTX 580, but this was the top of the line when I was at least experimenting with my OpenCL. These are the two standards. At the time I did this presentation, I was more interested in OpenCL because it's an open standard and that's awesome. But unfortunately, most of the packages that I deal with simply want CUDA. So for that reason, I tend to stay largely on the Nvidia line. That's simply what works with me. I realize choosing one of the premier graphic card over the other is a somewhat politically charged statement, but I deal mainly on the Nvidia side. That's not that AMD is bad or anything such like that, but most of the stuff that I need works on CUDA, so that's where I have to stay. So the reasons to choose CUDA is direct support for BLAS. Now BLAS is a linear algebra package that you can do that on CPUs too, but you don't want to write your own linear algebra package. It's good to make use of this, and this is what what TensorFlow makes use of. So CUDA has a direct support for that, and it works quite well. The reasons not to choose CUDA is you're locked into Nvidia, basically. And it doesn't have as good a support for mixing of GPU and CPU. That is one thing that OpenCL does that really is pretty cool. You can, and I don't know, maybe CUDA might be moving towards adding this, or they might have already added it. I don't follow this as closely on the OpenCL side, but you can literally take code that you wrote for the GPU and run it on the CPU. So it essentially emulates. So you can write your entire application targeting the GPU, and if the user doesn't happen to have one, it'll just emulate it on the CPU, and it'll work. It won't work all that fast, but it'll work. So that's kind of neat. I think it's neat that OpenCL can switch back and forth in that way. Reasons to choose it, somewhat like I said, it has wider hardware support. If you're only going to be targeting Nvidia, it's probably best to use Nvidia itself directly. So largely, it's just going to boil down to what does your software need. And at this point, late 2016, TensorFlow is using CUDA primarily or completely. This is much more of a Java-oriented slide, but it applies. I say LWJGL, that's what I was using for OpenCL on the Java side, but this would basically be TensorFlow. There would be no JNI, because that's how you go to native applications. Because at the lowest level, OpenCL or CUDA, this is all C and Fortran. Those are the two languages that it supports directly, and that's it, because those are some of the most performant languages you have. Believe it or not, if you don't do a lot in the low level sort of mathematically intensive computing, Fortran's alive and well. There's packages that you will use in R and Python that were actually compiled in Fortran, because that simply is the best language is the language that some of this stuff was written on, and they work just fine. So the Python code is exposed up through Python or R, and you're able to make use of that. But if you want to use OpenCL or CUDA directly, you're programming in C. And the little kernels that you're writing that execute on the GPU are also written in C. And it's a very different sort of programming style. And like I'm saying, native code must be used. You're not accessing this GPU directly from Java, Python, or R. The languages provide the ability to connect through that. These are just options for Java. This really doesn't apply to this class. Doesn't apply. So these are just other options that I was discussing at the time to use. There's been a lot of interest in just writing code like this a priori initiative that AMD was creating, which I haven't seen got a whole lot of traction, but it might still be going. The idea was that the programs would analyze your code and be able to generate GPU instructions just from your normal code, because writing GPU code, the low level, is very difficult. Very, very difficult compared to Python, even compared to C. So it's, even though you're writing in C, but you're writing in this sort of subset of C that makes it very difficult. There has been some AI projects that are very interesting that look at writing and optimizing GPU code. But largely you're either using TensorFlow, which has already done all this hard work for you, or you're handcrafting your own GPU kernels. So the GPU kernel, fundamentally, this is the little block of code that is executing on the GPU. So when you're writing actual GPU code, you've got code that's running on your computer called the host, and then you've got code that's running inside of the GPU. So the kernels, and you need to copy because the GPU has its own memory. So the kernels are executing on the GPU, and the data need to move back and forth between those. This is some example kernel code. So this is actually OpenCL, but it looks very similar to the CUDA type code. Here, they're basically, I think this is doing a fast Fourier transformation, but you can see, this is not high-level code. This is very low-level kind of C, in this case C99, the 1999 edition of C, which is not out of date. That's actually, that's the kinder, gentler version of C, but it's still C, and it's still dealing with pointers, and you're dealing with all of the extensions. I did spend quite a bit of time trying to get my own incog machine learning and neural network framework. Oh, quite a few years ago, maybe around 2013, I was working on that. I was trying to actually write the handcrafted kernel code. I got it executed and working on the GPU, but it's very, very difficult to use compared to traditional programming. I recommend using very much something higher level like TensorFlow, where you've got a team of people who are working on handcrafting these kernels. Designing kernels is very, very difficult. Memory transfers are expensive. They take a lot of tweaking. You can't branch in these. You don't want to use if statements. You will literally sometimes use mathematical equivalents to get away from having to use if statements like coefficients of 0 or 1 to turn certain parts of the equation on or off. Memory optimization is huge. There's several classes of memory that are available. And registers, you have a ton of registers on a GPU, hundreds. So you want to use code as local variables, which typically gets compiled into registers, and that will help it. These are massively parallel. You have hundreds, if not thousands, of cores working on the GPU, but they're very limited, so that's why the if statements don't work. The cores have to be doing largely the same thing. And you can deal with multiple GPUs. So the big things to keep in mind that are hard for a GPU is transferring data back and forth is difficult. You can use pinned memory to sort of pin some of your main memory so that you can speed up some of this. There's a lot of tweaks. Again, if you're dealing with TensorFlow, they're doing all this low-level stuff for you, which is really nice. This is the one that I found the most frustrating when I was programming GPUs, is you just can't use if statements. So that little picture I have there, that's a farmer plowing the field with a tractor and if you've ever seen plowing happen, there's all these blades. Well, if there's a big rock in the middle of the field, it's very difficult now. He can't just have some of the blades go around it. The blades are all operating together, so he's got to stop that entire tractor, move around it, and get around it. Those rocks, those are like the if statements. The cores need to be doing all mostly the same thing, or it's not going to work all that well. And then lots of memory optimizations. There's several classes of memory, and you spend a lot of time dealing with those three classes. There's the global memory is the slowest, and you deal very much with reading and writing memory. Writing memory, especially that global memory, is very slow in the GPU. So you typically load your data set there because you're only reading from it, and that's a lot faster, but you don't want to be doing any sort of scratch padding where you're changing data frequently in the global memory. But it's unfortunately the biggest. Your register memory is the fastest, but it's measured in kilobytes, not gigabytes. So that's an issue. Best practices. What's interesting is when you look at all the nice coding standards that they tell you for writing modern software on Java and Python, it's all very different on the GPU. Performance is king. So reuse your local variables. If you have typically they'll tell you if you used a variable A earlier in your function, don't reuse A. Use a whole different variable so that you're not mixing meaning. But those are your registers, so reuse them aggressively. And you typically only have about 32K of local memory, so you'll use that as a scratch pad. You'll be reusing it constantly and reassigning it throughout your kernel usage. And 32-bit floats instead of doubles, they're faster and they take up less memory and minimize branching standards. So really there's no sort of coding. Prettiness of code is not the goal here. The goal is to make it as fast as possible. And again, if you're using TensorFlow, luckily you do not have to deal with this low of a level. And this is just some of the this is OpenCL, but CUDA is somewhat similar, just in terms of the memory hierarchy. So global memory at the bottom is the slowest. Your private memory at the top is the fastest. So this is critically important in GPU programming, is your different classes of memory. This really doesn't exist in CPU programming. So this is hard to get used to. And yeah, this is just some code that I demonstrated to do this. Basically, this is the same laptop, my 650M, and I was basically just showing how to do something very simple. So I was adding two vectors. You see, basically at the bottom, 1.02345, and then I added to 9876. So I'm adding one vector increasing, one vector decreasing. So 1 plus 9 is the 10 at the bottom, and they all add up to 10. So 10's all the way across. And I show that basically you can execute this on a separate machine. So we've already gone through a lot of this kind of stuff. So yeah, that's it for that presentation. But that just shows you what's going on inside the head, so to speak, of a GPU. So if you're doing true scientific computing and it's not deep learning, you might well be programming the GPU directly. And there's a lot of good books on that kind of thing to do, but unless you like C programming with pointers and all that sort of thing, you probably won't like programming the GPU directly. Fortunately, if you're just dealing with it in TensorFlow, the hardest part that you're going to have to deal with is actually getting it up and running. And that's what I am going to show you a little bit of now. Once you have all of the components installed for the GPU drivers for Nvidia CUDA, basically what it's giving you is an additional C compiler. So one way you can quickly test and see if this is actually installed or not is if you just go to the command prompt, and if you just type cc, that's your C compiler. Any Unix system that has the dev tools installed is going to have something like this. So you just press cc, and that's the C compiler. It's basically telling you clang, no input files. Now, if you do NV for Nvidia CC, that's the Nvidia C Compiler, and any program that is going to work in conjunction with the GPU, low level, is compiled with this. Now, in the background, this is actually what TensorFlow, and you can see it there, it's basically telling you a few warnings about some GPU targets that are going to be deprecated, but it does show you that the Nvidia C Compiler is installed. So when you're making use of TensorFlow, what TensorFlow is really doing under the covers is it is actually creating those compute graphs and essentially building compilable C code for your neural network that you've created. That makes it very, very fast because it can use C and it can use the underlying Blaze linear algebra packages. all those together make it very, very fast. So having the Nvidia C Compiler there, that's all that TensorFlow does to support the GPU, is it switches over and it uses that C Compiler. It's not magic. You can't take just normal C code and suddenly compile it and it's going to work on a GPU. There's extensions to it. So if you've ever used Oracle's Pro-C, where you basically can inject Oracle code right into a C code, this is using essentially the same sort of technology. It's a pre-compiler to C. Now that we have that, we want to try to run a couple of examples and see if those actually work. So I have those already installed. They come with basically the download packages. So if you change into the CUDA Samples directory, you can see all the samples that they have provided there. That makefile can be executed to build them all. I already built just a couple of them that I wanted to use for this demonstration. So if I move into the bin directory, and then you can see basically that's the platform, and then it's Darwin because it's Mac. And there we go. And then release. So these are some of the compiled packages that are compiled examples. So remember I showed you that vector add? That's a very common one. We saw that in the slides from the OpenCL. But if we just run vector add like this, vector add, then it shows you basically that it did sort of an addition, and that worked just fine because it keeps track of that. So it tells you that this particular test passed the test. Now, if we look at another example that's in here, yeah, let's see. I can make that bigger. Makes that easier to see. So we can also do the device query. This is a pretty cool one because this shows you what CUDA devices it can actually see on your computer. So if we run that, it scrolls off, but basically at the bottom here we see CUDA Driver. We can see the driver version 8.0, which as of the recording is the latest, and that is supported by TensorFlow. And I'm using TensorFlow 0.12 for this, which as of the recording of this was the latest. And you can see my driver is this GeForce GT 650M, which is a decent mobile GPU. The Microsoft Surface has a fairly decent, even a more advanced one than this GPU available to it. It's just I can't use TensorFlow on it. So if they ever add Windows support, my other computer is a Microsoft Surface, so that would be Surface Book. So that would be very, very useful for that as well. But you can see basically some of the information here. It has a gigabyte of memory. There's 384 CUDA cores, so it's got quite a few cores. You can't think of these almost evenly as CPU cores. One individual CPU core does a lot more than a CUDA core, but and you can tell the speed too. It's 900 megahertz, so lots of them, not as fast as a CPU, but they taken together they can do quite a bit. And most data comes into it as a multi-dimensional array, so this is the sort of maximum size. That's for texture, but the input comes in this size. So it shows you a lot of the information about the particular GPU card that you had. If you want to just test to see if your GPU card is functional, what can be good to do is basically run the... Now, I don't have the GPU actually enabled on my Python environment because I use Python environments, which are easy enough to set up. Basically, you... and I have a link to an article that I wrote about how to set up Python environments, but you can find many, many tutorials on those. But on Mac, you just type source activate TensorFlow, this activates my version of Python that has TensorFlow running or installed. And if I test this one, this is without the GPU. If I just run my Python test script, which is nothing that elaborate, all that this is doing is it's basically just doing a vector add in TensorFlow and runs the output. There's nothing GPU about this, although just depending on which version of TensorFlow we run it in, it'll either use the GPU or it'll use the CPU. So if I run that, helps to spell Python right. It basically fires up TensorFlow and it does its vector operation. And you can see it is basically, it's telling you outputs of what it's doing, and it's telling you that it's using the CPU. If I source activate GPU, that's just the name of the environment that I created that has TensorFlow installed for GPU. Now, if I run the same test, it's going to actually invoke my GPU. And you can tell, it looks quite a bit different. You see that it's invoking CUDA libraries, same exact Python code, same exact TensorFlow code, but now it's running the GPU. So it's telling me what it found. It found the GeForce. This is all sort of logging information that TensorFlow throws at you. TensorFlow is very wordy with its logging information. But this is how you verify truly. Just run that simple Python script that I showed you on the screen, and it will let you know very quickly. And it's also in the Jupyter notebook for tonight, back on GitHub, so you can get the code there easy enough. So now I want to show you the difference between running it on a CPU and a GPU, how you can really tell sort of the difference in. So let me show you one other thing too. This is my test GPU. This does the minced digits that we've seen before. This does a convolutional neural network on them and trains it, and it goes for quite a while to actually get done. It takes, on the CPU, it takes about an hour and 30 minutes. On the GPU, it takes about 30 minutes. So obviously, I'm not going to run this completely through right now on the laptop because I don't want the video to be that long. And I want to show you too, I'm in VI, so I can edit it, but you know how I said it was very loggy? It puts a lot of information here. This is how you set the logging level back so that it doesn't show anything. If you set it to 2 like I have here, it is going to only show you warnings and errors, but I do want some additional logging information. So what I'm doing there is I'm turning that back to full logging, so it'll be very, very talky to me. So what I'm going to do now is source activate TensorFlow. So now I'm using the CPU, and I'm going to run the test GPU. And again, there's nothing specific to the GPU in this code. TensorFlow under the covers handles all of that for you, so that's very nice. So I'm going to run it, and it's now spinning up my CPU. It is. You'll see those checkpoints happen a lot. We'll wait till it sort of gets into its main stride here, and I'll show you what I want to show you. And yeah, it's doing a checkpoint. It should be showing some logging information as well, but let me show you basically the activity monitor. So if you're watching the activity monitor here, you'll see that basically my system is now at 63% utilization. So it's pegging it pretty good. It's not using 100%. TensorFlow often does not use all of it. It just depends on the nature of your data and that sort of thing. There might be some configuration options that I could set to make it use more of that, but I've seen it use much less than this and much more than this, depending on the nature of the data. So what I want you to see here is when we're running it on CPU, what this load actually looks like. So you can see it's decently loaded the CPU. Now this would go on for about an hour and a half if I were to let it completely run. I don't really want to do that, so I am going to go ahead and stop it here. And I broke it. So basically now you can see that the CPU load is dropping to 0. You probably can't hear it through the microphone, but while that was going on, my fan was going basically at full bore. So that's because it was running completely on the CPU. But the GPU also will kick in a fan on my laptop. I'm not entirely sure if it's the same fan, how that works on a CPU, on a laptop. On a desktop, they're definitely different fans. But let me source activate GPU. And if I run that, now if I run it, it's going to do the same sort of setup, but you can see the CUDA stuff flashing by. So this is definitely using CUDA. And now it has, it's launched up and it is running. It's doing the first checkpoint. And it is beginning its process. It'll be full, it's probably full bore into this right now. But look at the CPU load. The CPU load is minuscule. There's nothing going on hardly with the CPU. We're at about 85% idle. So definitely there is some CPU activity handling the individual steps of training for this. But by all means, it is not going through there. I can hear my fan starting to spin up. So the GPU is working very, very hard, but the CPU is not doing all that much. I have not experimented with this very much, but what's fun to try is you can see that going there, and then you can start up a new window, and I'll make it bigger so we can see it too. And we do source activate CPU. I'm sorry, TensorFlow. And my fan's really going pretty good here because the GPU is being stressed right now. But if I go into my home directory where this file is at, and I do python GPU test.py, test GPU.py, typo there. So now this one's going to spin up on the CPU. So now I am effectively, so you can see it's starting to warm up, or spin up. And now I am really sort of beating the heck out of my computer because I have the CPU running full bore, I have the GPU running full bore. And it'd be interesting to do some real benchmarking with this. I don't know that maybe the CPU version, do either of these run slightly slower than the other? I suspect that since we're in the upper 60s of this, and now the idle's only 14%, I would expect that both of these are probably running at full speed, but I would have to do some further estimations and experimentations to find that out. But I think this is pretty cool. You can see it's higher than there. So there are gauges that'll show you how heavily your CPU is being your GPU is being taxed, but I don't have that installed. So this essentially shows you that I am now hitting both the CPU and the GPU pretty heavily while that's all going on. And I can still use my computer. It's a little sluggish perhaps, but if I go, so just to show you where this code is at, if you just go to my class website for the semester, And if you're looking at this for a later semester, I'll just have later versions of it. The videos will probably stay the same, but I will update the TensorFlow code to whatever is the latest. And if I go to the course content, and I go to AWS, which is what I called this because I was going to do this more based on AWS, but I changed it to GPU. But running this in AWS is all about the same. You just upload it and execute it. So this is this first program that I show you right here. This basically is the vector test. So this lets you test it just to see that TensorFlow is running. This code that I have here, the GPU definitely helps. I have code in here that will report the elapsed time. When I run it on the GPU, it's only 30 minutes. When I run it on CPU, it's about, well, not quite an hour and a half like I was saying, but it's about an hour 15 minutes. So GPU definitely helps on that. So that is all of the information on how to use the GPU. It's a very interesting topic. There is, for Amazon, they have some very interesting GPU instances. I have not played with the new P2 instances, but they are really cool. I'll show you the stats on them. But essentially what's going on here is you can see the GPU count. The P2X large, that's the one that I have played with to some degree, and it is very fast. I did not try that exact benchmark program that I showed you there, but I would suspect it would run it very quickly. The GPU count on this is just 1. There's 4 CPU cores, so you don't need all that many CPU cores, like you saw on the activity monitor. But it has 61 gig of memory, and this is how many GPU cores you have. Look at the high end. You can have nearly 40,000 GPU cores and almost a terabyte of memory. So this is, and the GPU memory is almost 2 gigabytes of memory. So this is a pretty insanely powerful machine. And I mean, it's probably close to, or if not supercomputer class. It's $15 an hour to make use of this. So that's realistic. I would not mind spending money on this for a couple of hours just to see if my code scales and to do some benchmarking on it. But so far I've not really done a lot that requires this level of processing power. My dissertation really didn't work well on GPU, so it would go up to, I would use 36 core instances on, I think it was around 36 core instances on Amazon, and that helped a lot. That let me go through a lot of test cycles. But I'm planning on spending some more time working with these instances to see really what I can squeak out of it. Because some of the neural network activity that I do, I can spend hours training. So if I could cut that down to a half hour or 10 minutes, that might be worth some of the money for this. I don't know that I would spend money on this. $15 an hour gets expensive, but if you think of that in terms of a human wage, that's not too bad to hire some. I don't know any humans that have that mathematical capability. So that's very interesting technology. So anyway, that is really all I have for this entire semester. This is the end of the course. I will keep this class is already set up for next semester, so I will probably, depending on if I'm using the data science workbench on IBM, I might even use Kaggle because they do let you run Jupyter Notebook instances now. And it works pretty well. I might use that in place of Data Science Workbench, not entirely sure. They do have later versions and keep up the versions more current. Now, granted, TensorFlow is changing just about every month, but that might be better. But the point is, I will keep the code up to date for the latest version of TensorFlow. I will probably branch and create a version for 0.12 pretty soon, because there's been a few changes. The core concepts, like I talked about in class, are all the same, but the actual coding in TensorFlow does change a little bit as they've optimized things and tried to make some things easier. So look for that on the class website. You will see that updated in the future. But anyway, that is all I have. So thank you very much for a great semester, and hope to see you guys in if I teach other classes here, or if our paths cross in the future, I will see you then. Thank you very much.